I have been using generative AI tools to write code since the day those tools first appeared. They write substantial amounts of code for me today, but besides code, they also make bugs. Not syntax errors or missing includes or something like that. No, I mean real behavioral bugs. Something is wrong in code, something that requires human intervention. Then, whenever I point that out, someone comes and says, "Oh, don't use that model, use this model." Then I go and use this model, and that model makes bugs again. They say, "Oh, wait for the new version, it will come by the summer, it will fix everything." The summer comes and the bugs are still there. I know why that is so. The story is very simple. Bugs are literally built into every LLM. They will never stop. But if you want to understand that, it takes a bit more effort, and that is what I'm going to show you in this video. I will show you what's inside the LLM, any LLM in existence, and I will show you what mathematical foundations on which they are built are making bugs inevitable. In other words, LLMs, no matter how well trained they are, will always make bugs. It's inevitable. We will remove all the refinements and tools added to an LLM on its outside and look into the bare model. When you peel off the chat interfaces, IDE integrations, agents, plugins and everything, you will find the bare model, and at the core of the model of every LLM lies a deep neural network, one or more of them. Deep neural networks are topologically equivalent to multi-layer perceptrons, and multi-layer perceptrons are historically the oldest topology of artificial neural networks. A multi-layer perceptron consists of layers, and each layer consists of neurons. Each neuron has multiple inputs and one output. The first layer only receives the inputs and does nothing. The transforms happen in each of the neurons. Each neuron receives its inputs, multiplies them by weights, sums those up and passes that through the nonlinear activation function. Do that for all the neurons in one layer, and you have the output of that layer, pass it on to the next layer, next, all until you reach the output layer and you get the output of the entire artificial neural network. Those weights by which you multiply the values, those are the parameters of the artificial neural network, and you will know them as the parameters of the LLM. The history is very interesting here. It started in 1943 with the first artificial neuron explained, and then in 1958 the first single-layer perceptron was designed. Then the multi-layer perceptron followed, and perceptrons with multiple layers, which we call today deep neural networks, were also built during 1960s. So the history of deep neural networks is not new, it's more than half a century old. But there is one very important detail which I must clarify before anything else. There is a distinction between training a neural network and running a neural network. Those two are completely different activities. Supervised learning, that is how we train artificial neural networks, such as those in the LLMs. A network sees large amounts of data on its input, and for every row of inputs there is a known output which it should produce. During the training, we adjust weights in the network so that the discrepancy between the actual output of the network and the desired output is reduced. That is training. It can take a long time and very complex algorithms, but once you complete the training, you get your model, and that's it. The training doesn't have any effect on the model anymore once you start using the model. And in that way, one layer of magic disappears. What does the artificial neural network do? It accepts the inputs, forwards them through the layers, produces the output, and that's it. You get your output. There's nothing special in it. The next token you want on the output, just pass the new input and wait for the new output of the network. That's all. Any knowledge the network might have is baked into the weights of the neurons inside of a deep neural network. And that's all. A better, improved training algorithm could make it cheaper to produce the new model, the next version of the model, with less compute power. That is very nice. It could also help make the model with less error. Well, that is intriguing. Can we make a new artificial neural network which produces less errors? Is that possible? And how much is it possible? How much can we reduce the error? Well, that is where the famous universal approximation theorem comes to the table, and we finally get into the mathematical background of deep neural networks. The nonlinear transforms of the neurons in a deep neural network are not arbitrary. They make the entire artificial neural network a nonlinear transform of its inputs, and that is very important because such functions have some provable properties. And the universal approximation theorem is pointing out a few of those properties which are very important for the theory of artificial neural networks. This theorem first appeared in 1989 when it was proven, and it didn't just come out of the blue. It's pulling its roots all the way back from mathematical theory of the 19th century. The first such attempt was the Weierstrass's theorem from 1885, and there were a few other theorems in the meanwhile, which eventually paved the way for the universal approximation theorem. And this is what the theorem says. An artificial neural network can approximate any continuous function on a bounded input range at an arbitrary level of accuracy. Now, what does that mean? Let's put it into practice. If you approximated probabilities of tokens, words in a spoken language, you can train the network to speak that language. If you train it on probabilities of the next token in a programming language code, it will write code in that programming language. That's what artificial neural networks do. They approximate whatever you have shown it on the input, and they try to produce similar or same things as they saw during the training in their practical use later. Can you see it now? The artificial neural networks are learning the statistical patterns of a language, and then they are reproducing those patterns when used. That's what they do. But then come the consequences. First, an artificial neural network never produces that without an error. While it can approximate a function to an arbitrary level of accuracy, it's never perfect. There is always error. Second, the outputs produced by an artificial neural network always resemble the outputs it saw during training. It cannot work on things it didn't see during the training. You cannot show an artificial neural network a book, make it read it somehow, and then write software based on the principle it learned from that book. That's not artificial intelligence, that's science fiction. That doesn't exist. Third, the network only has that level of errors, which we saw during training, on the bounded input on which it was trained. Move out of that input And the network will start making gross mistakes. Show it words it never saw, show it syntax of a programming language that came out after the model was trained, or show it a library it never saw during training, and the model will start hallucinating big time. That's how they work. It's built into them. So how does a large language model write code? It's essentially very simple. It takes the code it sees already, it takes your prompt, and then tries to predict the next token, and the next, and the next, and the next. And so it writes an entire line, or a function, or a block of code, whatever you wanted it to write. But there are certain aspects of this behavior which you must understand. That code which you are passing in the prompt has never been seen during training. The artificial neural network will always operate in the interpolation mode. It will always try to recognize fragments of somebody else's code it saw during training and then produce a fragment of your code. Therefore, output will never be exact. And then comes the revelation. Is that code correct? Is that code incorrect? There is no way for the model to tell. It requires a human in the loop to see the code and to tell what is good, what is bad. If a human doesn't notice an issue, then the bug will be there. But the universal approximation theorem also tells when we can expect bugs to appear. Stable error rates within the bounded region of the inputs are expected. That's what the network was trained on. But even there, the situation is not uniform. There are regions where millions of samples exist from which the network was trained. That is where the LLM will be confident. It will write perfect code for you because it had numerous other samples which it can interpolate and produce flawless code. But if you are working on anything experimental, on advanced algorithms, anything of that kind, then the real samples in the training set are rare, and the error rates will naturally grow. You cannot expect an LLM to produce anything exotic in your code with confidence. It will make many, many bugs. And of course, if you just step out of that region on which the network was trained, you can expect that the error rates will go wild. It will probably create more problems than it solves. The message from this analysis is clear. LLMs will never stop making bugs. No matter how large the model underneath is, no matter how good its architecture is, or how advanced the training algorithm was applied, what you see today is essentially the ceiling. That's what LLMs are. There won't be large improvements in LLMs anymore. That's my prediction. They will be faster, they will be more convenient, yes, but they will never become absolutely correct. They will keep adding bugs at some rate, and you will always have to be there to read all that code and to find and correct the bugs.